So hi everyone, welcome back to week 6 of Techquitable Futures. This week we'll be going over the topic of linked list. Adam, you want to hit next? Yep. And then for the agenda today, it's kind of composed in the following sections. First, we'll go over the definitions and basic operations of linked list. And then we have two sample problems that we want to go over with you. The first one being reversing a linked list, and the second one being detecting a loop within a linked list.
So my name is Adam Morrison. I'm a software engineer at Arista Networks. What we do is we make various networking equipment like routers and switches, primarily focused at the cloud and data center market. So I work on the software that runs on those boxes. And I graduated Rice University in 2019.
And hi everyone. Yeah, my name is Brian, and I currently work for BlackRock as a risk and quantitative analyst. So more of like a data science role than like software engineering role. So if you're interested in data science and data engineering, feel free to reach out to me or to enter, and then he'll get back to me on that. I graduated from Harvard in 2020 with a degree in applied math focused on computer science. And yeah, nice being here.
So we're going to start out with just kind of some basic definitions and operations on linked lists and figuring out how it works as a data structure. So first of all, why do we need linked lists? We already have arrays. So arrays, as you went over previously, are a continuous block of memory, so they have quick access to any index, but usually they are a fixed size, and the contiguous is the key part. So with linked lists, we don't use contiguous memory. We can take little bits of memory from anywhere, so it's really easy to allocate. And we just kind of stick them together by using pointers, which we'll get into in a little bit. And then the other nice thing about them is because we're just kind of sticking together little bits of data from everywhere and it doesn't have to be contiguous, this can be dynamically sized. We can always just keep adding more and more. We don't have to like go and copy over the whole thing into a new block of memory when we want to expand it. We never have to worry about reallocating and resizing things. You just, oh, you want to add something else? Here's a little bit more memory. Let's add it in. So how this works is each node contains, first of all, the data it's meant to store. So in this instance, this first node contains the data 3, but it also has a pointer to the next element. So the first node has 3 and then says, and the next node is at chunk 2. Then chunk 2 says, well, my data is 1, but I'm the end. There's nobody after me, so my next pointer is empty. So you could see that here in a little bit of a larger example. You have 3, which points to the node which has 1, which points to the node which has 4, which points to nothing because it's the end. And so then the only thing that you actually need to remember or like keep track of in your linked list, that basically the value that the variable will store, is the head, which is where the first element is. So you say, say I have a linked list variable that I named foo. Foo says, well, the beginning of foo is the node which contains 3. And then once again, 3 points to 1, points to 4, points to nothing. So when we're implementing this, we are going to effectively use 2 classes in Python. First of all is the node. The node, as we said, it's got the data value. So this will be 3 or 1 or 4 or whatever. And then the next pointer, which will be another node type. So, it will say this is the next node in the list. Yeah, okay. And so then our linked list class representing the larger data structure only has a head, and that head is itself a node type. This is the beginning of the linked list from which we can get to all of the others in sequence. Okay, so we are going to get into how to work with linked lists, how to do various operations on them. But before we do this, are there any questions on kind of like the basic definition and structure of a linked list? I don't know if I have chat open or if there's just not questions. So I'm just gonna keep going. Okay, So yeah, actually, real quick, just based off of what we know, so what I've mentioned so far, do we have any guesses about what the runtime of something like search would be? Oh, wait, there's chat's cool. Here's the chat. Oh, then, yeah, very good. And how about insert? Any guesses on insert? Depends on the place. But yeah, O of 1 if at the front. What if it's not in the front? What if it's in the middle or somewhere? You don't know where yet. Yeah. Yep, O of n if not. Very good. Okay, cool. So let's go ahead and look at some of the implementations. Don't worry about memorizing it. Just, have some idea about how they work and what the runtimes are so that you can use them effectively. Cool. So the next operation is very simple. It's just if I have a node, what's the next element? Obviously, this is O of 1. It's pretty straightforward. It's just node.next, or if you're looking for the value at the next, node.next.data. Since Python passes objects by reference, this is very easy. Tail is how if I have the head node of the linked list, what's the last node? And for a regular standard linked list, this is O of n, because we have to traverse the entire linked list in order to find what's at the end. And as you can see in the Python implementation here, the easiest way to do this is with a while loop. You just have your current node, and then you check the next one. And while there is a next object, you're not at the end yet. When there's no longer a next object, that's the last one. You return that. Now there is another type of linked list called a circular linked list or a doubly linked list. There are two different variations that can help you do this a little bit easier. But we will learn more about those in later slides. Okay. So now for the length, if we want to find the length of a linked list, it's pretty much the same, except instead of just returning the end of the last node that we come across, we keep track of the number of nodes we visited, incremented by 1 each time. And when we hit the end, we return the length instead of the last node. Pretty much the same thing, pretty straightforward. And from here, Brian is going to take it over. So I will stop sharing and let him do that.
It sounds good. Thanks, Adam. Yeah, let me set this up real quick. And then let me start screen sharing. Okay, can you guys see my screen?
Yep, you're good.
All right, sounds good. Yeah, so the next operation that we'll cover is search. So for this operation, you're given a value in the linked list and you're asked to, so given the value and you're given the head node and you're asked to find whether this exists in the linked list. So how do you go about that? So what you basically do is you traverse the linked list using a while loop. And at every step, what you do is basically check whether the data that you have at the moment is actually the value that you're being asked for. So remember, as Adam mentioned previously, for linked list, we store two information. That is, one is the data that the node has, and the other one is the pointer to the next node. So in this, you just want to get the data of the current node and actually check whether it's what they're asking you for. And runtime of this, as you mentioned before, is O of n. And then inserting at head, yeah, that's a pretty easy one to do, because you basically just have to add something to the beginning of the linked list. And how do you do that? You basically create a new node, and what you do is you change the pointer of the current head. Or like, okay, so first of all, you create a new node, and then you actually have the pointer of that node point to what was previously the head of the linked list. And then that's it. Yeah, so pretty easy to do. And the time complexity of this is O of 1. And then what about delete? So if you're deleting the first appearance of a given value from the linked list, this will be pretty easy if the given value is actually at the beginning of the list. That's easy to do. But if it's like in the middle or even like at the end of the linked list, it becomes a little bit more complicated, because what you basically have to do is you have to keep track of like various data for you to actually implement this successfully. And so we'll see later on why you can do this more efficiently using something like a doubly linked list as opposed to a single linked list. Because for a single linked list, so for this example here, the code that we have right here just works for a single linked list. But what you basically have to do is you also have to store this variable called previous. And why is storing previous actually important here? You're storing previous because as you're going through the linked list, remember you're being asked to delete a node. So let's say you are at the current node that you want to delete. After deleting that node, what you want to do, you basically want to link, because after deleting the node, you basically have two linked lists right now and they're separated. And you want to link the previous one, so the one that just comes before the current node, to the one that comes after the node that you just deleted. And so that is why we actually have this previous variable, because that actually helps you like link these two linked lists together after you've done the operation. Yeah, so like it's a bit confusing. And also it's not immediately clear why you actually have to store this previous variable. But yeah, that is the reason why. Do you have any questions on this or anything before that? Let me see chat. Sorry. So yeah, so if there's nothing, I'll go to the next slide, which is doubly linked lists. So we had mentioned before what a doubly linked list is and what the applications of this is, but basically you just have a single linked list, and then you add pointers to every node. So like in the opposite direction. So for every node, you not only have a pointer to the next node, but also a pointer to the previous node. And this is actually very helpful because it actually makes certain operations like very easy to do. And we'll see on the next slide which operations these are. Yeah, so how do you implement a doubly linked list? So basically, it's very similar to what we had done with a single linked list at the beginning, what we showed you before, but here you just add self.prev, which is the pointer to the previous node. Yeah, so what are the applications of a doubly linked list? Remember we had said previously, like with the example that I showed you, if you want to delete or insert objects from the middle of the list or the ends, it might be very complicated, right? Because you will basically have to keep track of all this other information. And the example that I showed you with the delete function, you had to store a prev variable. But when you actually do this with doubly linked list, you don't have to store this additional information. And that is because this is given by that pointer to the previous node. So like you already have this information embedded in the nodes of the linked list. And so you don't have to, I guess, have to create these new variables to keep track of everything. So it might actually make your work easier, or it might just make it easy for you to actually write up a solution or just be able to actually know what's going on. And also the other application will be when you want to traverse the list in both directions. So remember, like for a single linked list, you can only traverse the list from the head node to the tail, right? So just one direction, because you only have pointers in one direction. But for certain problems, you might want to traverse it in like both directions. So also like from the tail to the head. And also like we'll see in some example problems why you might want to do this. And this is where double linked list comes in. And then as we mentioned also at the beginning, we have circular linked list, just another variation of double linked list. But you just have an additional pointer from the end of the linked list to the beginning of the linked list. So you just have one more node than a double linked list, as you see here. So any questions so far? Okay, see. Okay.
Seems like there's no questions so far.
Okay, if there's none, I'll go to an example problem. So the first problem that we'll do is reversing a linked list. I'll go through this and show you two solutions to this and why one might actually be easier than the other. So this problem basically, for this problem, you're basically given a linked list. So the problem statement is this: you're given the pointer to the head of the linked list. So something that looks like this. You have nodes 1 till 5, and then the goal of this is to reverse the linked list. So you have the output as what is shown below. So you basically have 5 as the head node, and then you have pointers going in the other direction. So like at first glance, this actually is a pretty complicated problem to solve, right? Because you actually have to keep track of different information, of different data as you're going through the linked list. And I'll show you 2 solutions to this. So the first one is recursion, and the second one is iterative method. And so yeah, so the first one is recursion. So I'll go through this, and what this basically does is, yeah, so you're given the list, and the first step is you divide the list into 2 parts. So the first part is basically the first node, and then the second part is the rest of the linked list. And then you call the function again, so the function that you have reverse for the rest of the linked list. So you keep doing this basically until your linked list is fully reversed. And then the last part of the function is basically fixing the head pointer. So I'll just show you this using diagrams, because that's actually easier. Because it might actually be very hard to actually understand like recursion as a solution to anything, but using graphics actually helps a lot. So I'll go. So yeah, so step 1. You can see here, so we have a linked list here that has the head node as 1, and then you have 2, 3, 4. And for this step 1, remember, like we said, step 1 is dividing the linked list into 2 parts. So you have 1, that is the first part. So you can see the upward pointing arrows that basically shows you the 2 parts of the linked list. So the first part is 1, the second part is the rest of the linked list. So 2, 3, 4. So what is step 2? Sorry. For step 2, we basically remove the link. So the link going from 1 to 2, and then we create a link from 2 going to 1. So let's see here. So you can basically see. So as you're calling reverse, like on the rest of the linked list, like what it basically does is this piece of code here at the beginning basically just changes the arrows of the pointer. So for instance, you had the pointer from 1 going to 2, but now you have it going from 2 to 1. So you basically do this like at every step of the way until you have a fully reversed linked list. And then the last point is you fix the head of the linked list, because previously we had 1 as the head, and then but now we want to have 4 as the head. So that is the last step of the process. So don't forget that, because that's a very crucial step. Otherwise, your linked list won't work. So we have the Python implementation here. I think I'll actually advise you guys to go and try this by yourselves at home, because I think it's actually very helpful in you understanding how linked lists work in general. And also this is like a very common like interview problem. So I think actually practicing it on your own will have you become more comfortable with this problem. So are there any questions on this before we move on? Sorry.
Just a
Okay,
heads
so-
up, but yeah, if you're not feeling comfortable with recursion yet, don't worry. Our next presentation or next lesson is going to cover recursion, so you get more practice with recursion through that lesson.
Yeah, that sounds good. Yeah. And so the next solution will be the iterative method. So this is actually, I think, easier to understand, because recursion usually it's pretty complicated to understand for most people. So the next solution is iterative method. And for this, I'll show you how you do it. So for this method, what the crucial things that you need to do here is you need to have 3 pointers initialized at the beginning. So one of them is prev, which stands for previous, that is initialized to null. Then you have the current, that is initialized to the head of the linked list. And then you have the next variable, which is initialized to null as well. And so it's basically like an iteration through a loop. And in the loop, what you basically do is, remember, like you initialize next to be null. So before changing that next to be So before actually changing the next of current, what do? You store the next node in the variable next. So remember, like next is initialized as null, but then in this loop, you change that to be the next of the current node. So in this case, since we were given head as the current, you change that to be the next of the head. And then now you change the next of current. And actually that is where like the actual reversing happens. So changing the next of current, you basically change that to be the previous one. So you can actually see why we store prev, right? Because remember, like you're reversing a linked list, and so you want to keep track of the node that comes before us, because you want to change the pointer of the current node to be the previous one. So that is why you can see we have the variable prev initialized. That is its usefulness here. And then after you've done that, the actual reversing, which is basically just changing the pointer to be the pointer to point to the previous node, you just move previous and current one step forward. So you basically go through the rest of the linked list until you get to the end. And I have a GIF here, which actually shows this very well. So this GIF here. So you can see you've initialized prev and head and next to be null. And what you basically do, if you follow this while loop, it basically, I think the most important step to actually see here is the second line here, this one here, where you change the next of the current to be the previous one. So actually that is where the reversing happens. And then you basically move previous and current forward and for you to go through the rest of the linked list. And so this solution, just like the recursion solution that I showed at the beginning, have a time complexity of O of n, and that is because you have to go through the entire linked list for you to reverse all of it. And then this one has a space complexity of O of 1, right? Because you just need to initialize previous, current, and next. You just need to store those 3 variables. So that is constant space. Any question on this method? I feel like actually this GIF is very cool because it actually shows you like what's happening like very well. So you can actually go and review this afterwards if you want to understand this better. But I think it's a very cool GIF. Let me see if there's something in chat. Oh yeah, thanks Eduardo. Yeah. So any question before I pass on to Adam, who will take us through the second problem?
Yeah, I have one question. So let's say you got this question on as an interview question, right? And would your first step be, even before first doing this, would your first step be, I guess it depends on the kind of question, but would it be like first creating like a node class to then actually recreate the linked list? Or I guess it depends if they just give you the linked list to begin with, right?
Yeah, actually, yeah, that's a very good question. And I feel like that depends mostly on the interviewer's goals. So they might actually assume that you probably already know how to implement a linked list. So they don't want you to like come up with that from scratch, but others might actually want you to actually like implement your own linked list at the beginning, just so they can also test whether you have a good understanding of what linked lists are. And so I think the best thing to do in that case is to actually ask the interviewer like clarification questions on, or do you actually want me to create my own class, or should I just assume that that's given to me? Also, that shows that you're actually engaging with the interviewer. So that's a good thing to do. Yeah.
Yep. To add on to that question, yeah, like as Brian said, like yeah, it could go both ways. Like this is just my personal guess, but most of the time, the interviewers would give you like a pre-existing like data structure for you to work on, and then it will have like these like basic interface, like things like prev, next, or data, stuff like that. So then you can just focus on, okay, how are you gonna update the pointers, or how are you gonna update the data using those data structures. But then I guess there are also some possibilities in which like they might ask you, hey, can you also implement from scratch, which also should just come fluent to you after you know how linked lists work. I mean, like this like node data structure is fairly easy to build, given that there are like 2 or 3 main attributes that you need to set up. And after that, it's all about like managing the pointers. So, and then, yep. So it was a good question. And Marie also had a question. She asked which is more preferred, the recursion or iterative. But yeah, Adam, O'Brien, if you have any perspectives on it.
I mean, I guess like preference in these solutions usually is a matter of which one is more efficient, like in time and space complexity. But actually, as we saw for these two solutions, they have the same time and space complexity. So there's really no preference here, like in terms of efficiency. But I feel like for me, like I actually understand the iterative method better because it's actually more intuitive to me. So just like a personal preference, but I guess computationally, they're the same in terms of efficiency. Yeah. I don't know if Adam has a preference.
I generally prefer iterative over recursion, not just because it's easier to understand, but you also just don't have to worry about things with stack calls. The general thing in pretty much every programming language, every time you do a function call, there's a whole bunch of stuff allocated in order to actually do another stack frame and set up all of that function call, which in most cases is really minor, especially here. Honestly, so I think this recursive solution was tail recursion, if I remember correctly.
Yeah.
And so actually in that case, most modern compilers will actually optimize out the recursion and turn it into an iterative equivalent for that very reason. So at the end of the day, they're actually like extremely, extremely equivalent. But if you're dealing with a non-optimized compiler or just anything else, just like recursion gets into a bunch of messy stuff with stack calls. So I tend to go for iterative if they're both the same.
All right. Do you have any other question? Okay. If none, then I'll pass it on to Adam, who will take us through the next question. So I'll just stop screen sharing so Adam can take over.
Okay, do that real quick. Have to get all the way down. Okay, so the question that I'm going to be taking us through is how to detect a loop in a linked list. So here, given a singly linked list, how do we detect whether or not it contains a loop? And so loops can come in a couple different forms. You see we have the one on the left and the one on the right. The one on the right is like a full loop, right, where the last node links to the first one. But the one on the left is what I'm going to call a partial loop, where the last node links up to somewhere in the middle, right? But the point is that for the last node, instead of the next ref being empty, it points to something else that's already part of the node. So if you're trying to traverse it, it's going to go infinitely. That's a problem. So how do we do this? Well, the kind of more straightforward approach, which is not quite optimal, we'll get into that later, is we just maintain a list of all nodes we've seen before. And if you see it again, it's a duplicate. And actually, the runtime can be very different depending on which data structure you use to store your scene collection. And we'll get into why in a little bit. But the Python or pseudocode implementation is actually identical. So you have your scene collection, whichever data structure you use for that. You start at the head node, as you do for linked lists, and then you traverse it. And if you look at the data for your current iterator or your current node, and if it's in your scene collection, you're done. You know there's a loop in there. That shouldn't happen. Now, if you haven't, then you take that data and you put it into your scene collection. And then you go on to the next iteration. I'm actually just going to go ahead and throw this out as a question. Why do you think this is O of n squared if you use an array, but O of n if you use a hash map? I think I see a hand raised for somebody. I'm not super familiar with the Zoom, and I'm forgetting how to pull up chat while I present it. Here's how I pull up chat. Anyone have an idea?
Yeah, you said Wait, I have a
I think-
question. Is that a hash map or or is it a set?
So it is a dictionary in Python, which is
Oh, right.
effectively a hash map.
Got it. I got confused with the syntax sometimes. All right.
Yeah, that's no
I
problem.
think because in the hash map, it's just quicker lookup.
Yep, exactly. A hash map has O of 1 lookup, whereas an array is O of n lookup. So that first line under the while loop, if iterator.data in scene, if you're using an array, that one line is actually O of n, where n is the length of scene, but scene can be as long as n. Actually, I think instead of O of n squared, it would be more like n times n factorial or something like that, because scene isn't just always the size of n, it actually does grow linearly. So your first one will be a 1, then 2, then blah, blah, blah. But anyways, if you're using a hash map, that will always be O of 1 lookup. And so it's just O of n because you're just iterating over it. Now, there's a second kind of fancy solution to this that we're going to get onto. I'm going to take you through it before I explain the intuition, because I think it'll make a lot more sense after you've seen it go once. But the basic idea is that you keep 2 indexes into this. You can basically keep track of 2 nodes, your slow node and your fast node. The slow node increases by 1. So here in your first step, it went from 1 to 2. And your fast node increases by 2 every time. So it goes from 1 to 3. So it skips 1. And then the idea is that if they are ever equal, if slow and fast are ever the same node, you know you've hit a loop. So let's go over this just through one iteration. And the next step, slow moves from 2 to 3, and fast moves from 3 to 5. Then slow moves from 3 to 4, and fast moves from 5 to 3. So here we've actually gone over the loop, right? We've gone back to 3. And then finally, whoops, something, that one moved all over the place. Okay. Well, and then finally, we go from 4 to 5 and 3 to 5 into the same thing. So we know we've hit a loop. So this has O of n runtime complexity and O of 1 space complexity. So it's a little bit better because even though it has the same runtime as the hash map version, you aren't using O of n space. Now, how do we even know that this is always going to terminate, let alone that it's going to terminate in O of n? That's kind of complicated. But we're going to go back to, sure, let's take this slide, why not, to try and explain this. Okay, so here, if we don't have a loop, if there's no loop, it's very obvious that we're going to terminate with a false, right? Because fast is just going to hit. If we go back to here, we see that if the fast.next is false, we just return false, right? Fast is going to hit the end of the loop. We've hit the end of the loop. There's a null. So we know there's no loop. But here, now we've hit a point where both slow and fast are inside of a loop. Because it's a loop, even though fast is ahead, fast is also behind, right? It just depends on how you look at it because it's a loop. If fast is behind, then because it goes faster, it's going to catch up to slow. But it's not just going to catch up generally, it's going to catch up specifically at a rate of 1 node per iteration. So if slow is increasing by 1 and fast is increasing by 2, every time it's going to get closer by 1. So you see here, it's 2 nodes away, and here it's only 1 node away. Because it's catching up by exactly 1, it's going to hit 0 distance away, which is when they're equal, right? So if it was doing something like skipping by 3, then you could skip over it, right? So say you're 4 away and then you increase by 3, now you're 1 away, and now suddenly you're 2 over and you're back behind again. But because you're getting closer by exactly 1 node every time, it's going to go 4, 3, 2, 1, 0. You will hit a point where they collide. Not only that, but you're actually limited in how many steps it's going to take before you catch up by how long the length of the loop is, right? So so if we consider the starting point as when it enters this loop, the maximum amount fast can be behind is the length of the loop, right? I mean, technically it's the length of the loop minus 1, because if they're both on 3, for example, then they'd already be colliding. We'd already say there's a loop. But if you're on the maximum you could be behind is if slow was on 3 and fast was on 4, and then it would be 2 behind, and so it would take 3 steps to get to 0. 3 minus 1 minus 1 minus 1 hitting 0. And so that's how we know it's going, not only will it guaranteed terminate, but it will guaranteed terminate in O of n time, which is not intuitive at first. It actually took me quite a long time of staring at this to figure out that explanation, but I hope that makes some sense. Yeah. Are there any questions on this solution? Or on the question in general? Okay. Yeah, I think I didn't really go over the Python implementation very much. I was more focusing on the intuition, but just real quick with this slide, you can see exactly here where making slow is slow.next, fast is fast.next.next. If there isn't a fast.next, well, then we know we can terminate. And if they're equal, then we know there's a loop. And if they never equal, I mean, we're either going to hit the else case where we return false, or we're going to hit the point where we equal. That last return false after the while loop will never be hit. Yeah. Okay. So,
just to add on to this kind of like topic here, this like technique of using a slow pointer and a fast pointer also shows up in like other places. So it's like really nice trick to know. So I mean, as Adam kind of demonstrated, it's really helpful when you're trying to detect a loop within linked list. Also, it could also be helpful when you want to find like the middle of the linked list without like knowing upfront like how long they are. And you can imagine like using this technique so that by the time the fast pointer that moves like 2 steps at a time has reached the end, you will have the slow pointer arriving exactly at the middle of the linked list, right? Since one is moving 2 steps at a time and the other one is moving exactly half or 1 step at a time. So it could also be really helpful to do that, yeah, in that problem as well.
All right. So yeah, as Wentao mentioned, this is also useful for, or this similar sort of thing for finding them or deleting the middle of a linked list, finding the nth to last, removing a cycle. In order to remove the cycle, you have to detect the cycle, and yep. So for all of these reasons, those are similar questions that can help you to practice. All right. So now we're just general questions about linked lists, directed at me or Brian, whatever you want. Oh, wait, I see that Diana, you asked about nested loops. What was that in response to? Oh, how would you detect a nested loop? Is that what you're asking? I don't see how you could really have a nest. Oh, nested. Okay, I see. Awesome. Okay. Cool. Cool. Glad you're all good.
Yep. So does anyone have any questions about today's content, or any kind of career questions for Adam or Brian?
How did we get jobs? I'll answer this one first. So specifically, I work at a networking company, right? So I happened to do some networking research in college with a professor of mine. And so I had prior networking experience, and I got along with him really well. He really liked me, so he wrote me a very strong letter of recommendation. I will also say that if you're talking specifically about having trouble with recruiters, one nice thing about Arista, where I work, is that there's not really recruiters. The recruiters are the engineers. From the career fair to my phone screen to my in-person interview, everything was with engineers until my very last interview was actually with the manager of the Austin office. So that was nice. didn't have to go through recruiters. Yeah, I found out about them and I made first contact at my school's career fair.
Yeah, and then for me, yeah, I guess I'm so like when I was a sophomore, like I was mostly interested in like data science and data engineering kind of jobs. So as a sophomore, like I was just looking for programs that can make me like, I guess, get a role in that industry. And I think one of them was like, so like Facebook has this university program that they do for sophomores and first years, where they have you do something like an internship, but it's mostly geared towards, I guess, learning more than actually doing work. So like they train you for like about 4 weeks, and then they actually have you like do a mini project for another 4 weeks. And so like I reached out to the recruiters on this, and then they actually, yeah, like I did like a very short interview, and then I was actually lucky to get the program. And so I basically just took that chance to learn more about data science and data engineering while I was there. And then for my junior internship, I applied for a similar program, which I guess, and I guess like having that prior experience with data science and data engineering, that actually helped a lot. And then I see Eduardo has asked a question on working more on the data side. How does that differ from a software engineering job? Oh yeah, so that's a very good question. And actually data science varies like so much from company to company, as opposed to like software engineering. So it mostly depends on the scale of the company, like how big it is, and also how they plan to use that data. But I can give you an example of, I think Facebook is actually like a good example because they have like lots of data and they actually have a big data science team because that's crucial to their business. But I guess it differed more from software engineering, from software in that you also do a lot of analysis. So I guess as software engineering, you probably spend a lot of time just building stuff and building like, I guess, infrastructure. But for data science, there's like this analysis component to it. So I guess if you're attracted to analysis more, like, I guess, math and that kind of stuff, analysis more than actually like, I guess, building stuff, then I feel like data science is a good way to go. And also another way that it differs is also like what languages you use, which also says what Eduardo has asked the second question. So it's mostly Python, but also like some companies have like their own infrastructure and their own libraries which they use depending on their goals. But I guess just being familiar with Python is a good start because yeah, most companies use Python, and also when you're applying for these jobs, they'll test your Python knowledge because that is the most widely used data science language or data engineering language. Yeah, so I guess just to summarize, yeah, I guess it's different in that it's more analysis than actually building stuff. So if you're interested in that, then you can look into this, and also feel free to reach out to me in case you need more information. Yeah.
Yep, and then also to add some color to this like adjacent job of like data scientist. There are also like a lot of companies also has a role called data analyst, which could also be considered like more like a stepping stone to data science. So with like data analyst, like you would be kind of expected to know like language like mostly SQL because that's the standard language for getting the data out of the database and doing analysis. And you with data analyst, you will also be asked like to do like a lot of like answering business questions or even like trying to detect like a technical bugs with this product. If you see some metrics drop. So things like that, you need to like know SQL to pull the data out and be expected to like know, hey, how do I calculate like the summary statistics of this? Or how do I find this like, one specific metrics that we're interested in like, learning about? And I have also seen like with several years of experience as a data analyst, people also like learn like other languages such as Python. Also pick up more advanced topics in statistics, such as like actually like running like a correlation analysis or doing things like time series or actually building a machine learning model that it just enables those data analysts to switch into the data scientist role. Where those more advanced topics are expected from people in those roles. And I have also seen a bunch of cases in which like people move between software engineering data scientists. Like some software engineers I have known, they have done engineering for a few years and want to kind of get into the more data side. So they became like a data scientist. And I have also seen the other direction where data scientists, because they wanted to like write code, like more code and build products, they have moved on to the software engineering role. There are obviously some like, preparation or like extra training that you need to go through to make that switch, but it is possible given that the field is pretty fluid. So just a heads up for those who are thinking about either path. So.
So then, assuming we don't have any more questions, here are some additional resources. I think, Wentao, you said you had some more that you want to add to that list. I think I take it you'll just add them before you send out the slides, so that will be there.
Yep. Actually, I will take over the last 10 minutes here since we have extra time. Yep.
Do you want to share, or do you want me to just?
Yep. I'll share my screen.
Okay.
All right. Thank you guys. And let me find where my thing is. The slides. This is screen 1. Okay. Can you see my slide?
Yep.
Okay. So yep. So just a heads up, guys. So in appendix, we have added a lot of resources for you to learn about linked list. There are also these like lead code questions that we will recommend going through just so that you become more familiar with the operations around linked list. So yeah, I'll also be posting this in coding questions Slack channel, so you can also access them here or from this slide as well. And then, yep, since we have extra time, I can also kind of go over one more question. Just more focusing around like how do you even approach a question like this? So this question is on like removing a linked list element. Originally, we kind of wanted to like do this as a take-home exercise, but with extra time, we're going to go over them right now. So problem with this is pretty straightforward. What you want to do here is that you want to remove all elements from the linked list of integers that have the specific value. So in this case, we have a pretty simple linked list going from like 1 to with the data of like 1, 2, 3, 4, 5, 6. And we just want to remove like any node that had value 3 in it. So with this example, basically the next pointer of this like node with value 2 is going to skip over to this node with value 4, right? So then, okay, how do you even like kind of approach this problem? One really helpful tip or step to do is just you can think about all the possible cases, right, and see what you need to do with each one of those cases. So here I have like listed like different scenarios or cases. So case 1 is like linked list is empty. Case 2 is like all nodes have the target value. Case 3 is that somewhere like a node or middle nodes have the target value. Case 4 is that head node have the target value, which could also be different from this case number 3. And lastly, the last node have the target value, right? So you can kind of start to like when you get this question, you can like start to like brainstorm or kind of conceptualize the different cases and think about, okay, what are different solutions that I need to address each one of those cases, or are there like any solution that could work across like multiple of these cases? So with case 1, it's pretty simple. If the linked list is empty, then you just you can just like just return immediately, so that you don't need to do any like invalid operations, right? So that's a simple case. Case 2, like all nodes have target value, in which case like all elements should be removed and you return an empty linked list. Okay, now we're getting to the more interesting one, which is like any of the middle nodes have the target value. So in this example, I have marked like the node with the value was 3 and 4 originally. That's like the target value, but this X value is the one that we want to remove. And they're kind of 2 approaches you can take with this. Like one approach is like the look ahead approach, which is from the current value, you check to see the next node's value. And then next node's value turns out to be a target value. Then what you want to do is you want to skip to the next node value, right? So you want to have update the next pointer of the current node to current dot next, or basically 2 nodes away from the current one. So that would be like one approach. You could also do like the other approach, which is keep the previous node approach. So here you basically kind of constantly keep the previous nodes as a temporary variable. And if the current node has a target value, then you want to skip over that. So you can then set the previous node's next pointer to the next node, and then delete that element through that approach. And Yep, and then case 4, which is like, when you have, when your head nodes have the target value, in which case what you want to do is that you want to update the head to point at the next node until the next node does not have the target value. Right, that's what you want to do. And then lastly, with case 5, where the nodes, like last nodes have the target value, what you want to do here is that you want to set the next pointer of the last node to null, or to mark it as none, so that you know that that's where the linked list ends now. So yep, just wanted to kind of go through these cases with you and show you guys like a possible approach in which you can tackle a problem like this. Yep, so I would definitely also recommend going through these slides in appendix and try to see if you can actually think about solutions to each one of those cases in code. And if you're really curious, here's like a solution, then you can take a look and see if your answers actually compares well to this one. And lastly, there's also like another approach, which is this is also a technique that you can use with linked list, which is like introducing a sentinel, which is a fancy word for a dummy node. Yeah, basically the previous problem or solution actually requires us to provide a special handling for case number 4, or case when the head nodes have the target value. So for that case, actually introducing a dummy node that does not contain any data, but points to the the beginning of the linked list is actually helpful. And you can also see an example with this slide of how it's being used. So yep, just a heads up on those appendix slides. Let's see. Yep, so I guess that wraps the lesson for today. Any last minute questions before we wrap up? If not, well, thank you so much, Adam and Brian, for joining us today and presenting this lesson.
Thank you. I appreciate it.
Thank you so much for coming.
Thank you
Have
guys.
a good day.
You too.